Welcome to today's webinar. Today we give you an introduction to the new Dlubal API for RFEM 6. My name is Andreas Hörold. I'm responsible for marketing and PR in the company Dlubal Software. For instance, the German and English webinars, technical content of the website, newsletters, and so on. I will be the moderator today, and I will answer your questions during the webinar. My colleague Florian Hiddemann will be the presenter today. He's member of the product engineering team for RFEM 6. He knows a lot about the API for RFEM 6, and he's the main responsible person for the add-on optimization and costs. Okay, I show you how you can ask questions. At first, I switch off my webcam so you can see the full screen. If you have a question, just press the button with the question mark, then enter your question in that field, press send, and I will receive your question and I will answer you. The other way is to watch the entire webinar and email questions to info@dlubal.com. Okay, that's at the moment all from my side. I hand over to Florian. Florian, it's your turn.
Yes, thank you very much, Andreas, and welcome to our webinar to introduce you in our new API for RFEM 6 and RSTAP 9, R section 1 will follow in the near future. This is a Python-based solution to model, calculate, and get results in our well-known flagship software RFEM 6 for the start. And for the second generation approach here with Python, we choose a switch to another technology. Our first generation based on the SOAP protocol, and this as our second generation approach switched to gRPC with protobuf. And for you as a user, this means an enormous advantage regarding processing speed. From our internal testing, it is about 10 times faster in processing informations and steering commands than our first generation approach. But as every time, this really depends on your own use case and workflow you are actually using. So what would I like to show you in this webinar today? This is meant as a first step-by-step tutorial to get everything you need, get running, getting started, get a principle overview how this new API is working. We will have a look on the prerequisites you need on your system to start working with it, go through the installation process, how to set up the new authorization using API keys, and we will have a look on some boilerplate examples. And what you can see here, I prepared some units, some lessons to guide you through the new operations and how is it working step by step, really getting from a tutorial level to some examples for real usage in the program later on. And after we have an initial setup demonstrated and explained something about the principle, working with the RFEM objects, working with our input objects and the actual API commands, I will show you an example of a single span beam because we all understand this very well from a technical point of view and can focus then on the IT stuff around it. Maybe if some time left, we can have a short look into the class-oriented approach, working with this API on an example of a steer frame. And in the end, I would like to show you a nice example made by my colleague Robert Milrath, which is showing off a parameterized steel hall with a self-made graphical user interface, just to give an idea what is possible for modeling complicated and complex structures with our API. To give you a taste what is really possible with this, if you have no further experience with APIs in your background since now. In the end, as always, we like you to give a first glance in our next steps, what is coming next in the Dlubal API world. So let's start how do you get some information? Where's your point to look at if you are looking for documentations and so on? You can use our website, and we have quite a comprehensive documentation. Here our solutions, Dlubal API, and here with API documentation, you can jump into a separate area here on the website. This is your main source of getting started information and later on detailed information about the commands and model object itself. Everything which I will show you today here is in principle also available via this website if you have to if you feel the need to have a look on that later on. The application commands here for our package, they are available in this applications API part, and the model objects, and these are the messages, the content you are sending over the API commands, they are documented here. And if you are familiar with our RFEM structure navigator, it should feel some kind of familiar, because big improvement from my point of view is that we try to align the structure in the API with the structure of the program itself and the navigator, but I will show that later on in the demonstration. Besides of the examples here in the webinar, you also have here access to some other examples like a cantilever, silo, and some other nice models to get a feeling about the commands and what they actually do, as well as release information. So how to get the package, where should you go to use it, and how to install it? We use the platform PyPy to distribute our Python package, and maybe if you are a Python user, you are already familiar with it. Our package is known as Dlubal API, and here you can find the newest and latest versions, as well as other versions I will show you in this webinar. In the webinar, I will work with this version here from last week with the 2.11, and here with PyPy, I'm sure you know how to download, install it via this website. And later on, I will show you how I do it in my IDE environment to get an idea how easy and simple it is to get it running. What other prerequisites are needed? You need a Python version bigger or equal than 3.10. I think the actual version is 3.13 by now, and it is recommended to use an IDE for your programming and developing part here. In this webinar, I will use PyCharm, which is a brand from a program made by JetBrains. It is a free community edition here. And in our company, Visual Studio Code is also very likely. It's recommended for the internal usage here. So what is really important at first to have a look on is that the program version of RFEM is compatible with the package version from Dlubal API. I show that later in the program when we go to the installation process. And you need an active license for this product. Please contact our sales department, our salespeople. Write an email to support@dlubal.com if you are not sure about that. And then we can find some solutions for you. We are already developing some ideas how to get you a free testing access for your testing purposes if you are not ready to buy something here. But today we will focus on the idea what it is, how to use it, and how to get this run. So let's jump in and install the package we needed and get this basic setup in the IDE running. So what I prepared for you is this little project here with some units. We go from each unit to demonstrate some specialties around our new API. And in the first place, if there are nothing is installed yet, I can here in my IDE every modern IDE has something like this, especially the one which are supporting Python. They are capable to run and install the latest or special versions of the API package. So for this webinar here, I'm using 2.911. And we remember it is really important to have a look on the RFEM version of the main program version as well. If you can see here, the minor versions are both 9 and the patch version is also 11, which is equally. And this is really important because both the RFEM program and the Dlubal API package is released every week in a new version. And it is highly recommended to use the same version for the main program and for the Dlubal API version. The same version means the name convention is that the minor and the patch number, which is 911 here, is in both programs or both versions as the same. This ensures compatibility about features, special functions, and so on. And we try to avoid some unintended behavior by that. Of course, it is from a technical side possible to work with the older or newer version. That the RFEM version and the package version isn't exactly the same, but this could lead to very unintended behavior. And for production use or even for development purposes, it's not recommended to do that, to mix it up. So please have a look on that. So what else do you need to check if it's your first time using this? Go to your program options and check if this little checkbox here is activated. This is our new version for the API, the second generation. API service gRPC. This is what we call Dlubal API on the website, and which is our second generation. The old one by now is the web service SOAP, which is here marked as depreciated. And we can here, by click on this little icon, check if the server port is 9000, which is the default value for this. If it's activated and port 9000 is set it up, everything is right. And you can confirm that by clicking OK. So we have the package, we have the main program set it up. What else do you need? You need to authenticate with our new API. And for this reason, we go to the extranet, to your account. I already logged in here in my extranet account. And under this register here, API and Cloud, API 2, my API keys, I can create and manage all my keys which are used as kind of a password, as kind of a marker which let me access the API in my license. So what do you need to do? If you have a project, if you have something to work with the API, you can create your own API key. The license you will purchase is valid for the whole company. And if several users, several projects, several topics are working with the over the API, you can create several and more API keys than users and use cases in your company. And because we have a new billing structure, where some calls are they need Dlubal credits, to use them in the API. And with these API keys, you manage the sessions, the paid requests, and you can track the whole usage of the API in your extranet. So what I already did is I created a webinar and a second test key. And please do never share these keys to anyone else than yourself or your very high trusted colleagues in the company. Because if someone has your key, he can use it and do some operational business, and it will cost your money from your company in the mean case. So this is highly important. It's a security sensitive information here. So what I'm doing here, please never record this key in a webinar and distribute it afterwards on the website. So I will delete every key you can see here after this demonstration. So these keys here are important to authenticate you in the API code. So if you have created a new one, copy that to clipboard, and now I will show you how to set it up in your basic boilerplate. Okay, we have everything now. The package is installed, RFEM is ready, and we have an API key. So how to start with the basic usage? Luckily, we don't need so much code to start with. If you installed the Dlubal API package, I did this in a virtual environment here. It will install the Dlubal files here, as well as any other prerequisites you need and requirements. So everything regarding the API is now created in these folders. We will have a look later on in this folder for an important config file. So from this API package, you import RFEM. This is a very really important object, which most all of our others calls and methods and objects are used later on. So import RFEM is the single and important statement you need here to work with. And please, we recommend to use the with statements if you are new to this. This ensures that the connection to the RFEM program from the client here is opened and closed in a clean way. So we would like to initialize and connect to RFEM. I opened the program here in the background on the same computer as I'm working here. So we need 3 arguments at first. We need the API key value, which is the one I showed you in the first place in the extranet. And you need an URL and a port. You can see I took the standard port 9000. I'm working on the same machine, so is this localhost. And I set it up my security sensitive API key value. And with this, I call application method from the RFEM package, from the RFEM object, and use this later on as RFEM application, RFEM app. And what I want to do is I want to print some application info to check if the connection worked. So let's simply start and look what's happening. So for a short moment, we saw that RFEM was doing something, and we see on the right side, okay, the application, left window here, is answering his version, his language, ID, and name. And this example shows, okay, it was a successful authentication, and the connection was opened and closed like intended. And to ensure that this key is handled with a security from security point of view a little bit better, you have also the possibility to use an API key name as an attribute here in the method. So what we are doing now is we would like to mask the key itself and call it with a self-defined name, with my test key. And this is not the same I created here in the Dlubal extranet. These are separate ones. For this name here, I create a config file. How to do this in detail is also described in our documentation, the chapter here, access control. And I will show you here my virtual environment how to do it. You have to create a config ini file. This isn't created automatically. This is something you just can create in the Dlubal API folder. And in this config ini, we store our keys. And you can see here in lowercase letters, I defined my test key has this value here. In this version, this is not as a string value stored, it's just here plain what I copied from our Dlubal extranet. And if you have this config file and it starts with these brackets here, API keys, this is important that the program identifies it. Now we can use in the boilerplate key name this name which corresponds with this key. So let's try it again. If the connection is successful, we are working with key name, and yes, you can see we already get our application information. What's a nice other little feature? I would like to show you if I delete this line default and I run this program here again. Here automatically you will generate a new default key, and this is the last one you used here with these arguments. So it is intended to use this config file also with a default value, and this is the next example here. And you can see I also removed the localhost and the port information, so everything is running now with the default values for application. This is really a small and easy boilerplate. You just need these two lines here, the import statement and the with statement, to get a ready-to-use connection to RFEM. And what happens now is that if you run with default settings, this function here gives you back and prints what API key is used. And because of the fact we defined this as the default key, it looks back and gives you says, okay, I have used the my test key. If we want to change it and say, no, my default value in this project here is the webinar key, I simply change the config file, run this again, and can see, okay, now it is using as a default value this key, and it looked up and said, okay, this is called webinar in this config file. So from now on, every call with these every call of the application function here initiates a connection with my API key webinar. And I can also see this in my extranet account. And here you can see there was some test key calls, one with webinar. We do it again, run it. I created a new session using my webinar key. Can update here the table, and we see, okay, this session is used with the webinar key. So you have an overlook about your keys, depending on your user rights. You can see what's going on in the company, and you can also have a look on specific requests to say, okay, how much credit I used for some projects. So now we have everything in place to start actually working with the API and demonstrate the behavior and how the principle of operation and how to deal with models is working. So we are here by now. We managed the installation, the first boilerplate, and now I want to show you how to create some models, open existing ones, working with multiple models, which is a nice new feature. You don't have to create it on other ports as well. You can just work with a simple connection here. And after that, we have some example playing around with a single node and many nodes to get used by the idea behind functions and input objects. So how to open a model? We are just using now some basic API calls here. So I start again with the default settings. And at first, when I get a connection to the program, I close all existing models with this option, because we are doing it in the webinar now many times, and I don't want to have the question, should I save your model or something, as this is a safety feature that by default you are asked to close existing models. Are you sure? And we just close everything and create a new one where we say this is webinar new model, and we print the GUID of this new model here. So I will run this and open RFEM. But you can see what is going on. And in the right column here, you can see what the console in Python is printing. So this worked quite fine. We have a new model here. And like intended, we are printing now the GUID via the call getActiveModel. Every model which is created in the RFEM application gets a global unique identifier. So if you store or if you get this value for later work, you can change models with that and identify them in a session. If you want to work with multiple models, this is a nice improvement here. And I show you just a basic example what I did here to work with it. Let's say we create a Python dictionary which is able to store models. And to create a new one, I use the same function we saw in the last example, create model, and I call this model A. What I'm doing now is I store the value which I get back from this function here into the dictionary under the key model A. And this call here gives back the GUID, which you also can see by getActiveModel. So model A will have a GUID stored under the key model A. And I show you this key by asking the same like last example, getActiveModel, just to have here an idea what is happening. Then we will create another model. It's called model B, doing the same what this block here is doing. And then we print the dictionary with the keys and the values. The values are the GUIDs of these models. And then we can just switch to from one model to the other one, because model B is the last one which is created. This is now the active model then. And we go back to model A by using the GUID which is stored in our dictionary and asking, okay, set the active model to the model ID from model A. So let's see how it is working. So in first it creates model A, then model B. You can see this here, and then we switch back to model A. And on the right side you see it. Here's the first GUID of model A. This is the active one then. The second one, model B, is created with this ID. RFEM switch as an active model to this one. This is stored in our dictionary, and I can change back to model A with just a simple call. And if you are in an active model, every other API call is using this model for manipulation. So you can have in one connection working with several models switching back and forth and get your information by runtime in which model am I actually and where do I want to go. Another important use case to work with models if you have already existing models as an own RFEM file. So here in this example, I will open a model from an existing RFEM file. This is stored and set it up here as an absolute path. It's in raw string. And we will just make our connection and say, open the model from this path. What we can show just here. I prepared a simple example model. So, and we can see it opened and get his model ID back. So this model here is the which is prepared, and I set it up other units here as a model setting where you can see it's not a fresh created one. Important to say, we are working with SI units here for all input values and for all output values, which we see later on in the results. Okay, this is now the installation and getting started part, working with multiple models. Showed you these ones. And now we change to the principle of operation, let's say, how to actually work with RFEM objects. We will have a look on the mapping of the structure navigator and the API structure, and how to deal with the properties and make new objects and update them and so on. So if you are familiar with the RFEM structure itself, you will see that our API is trying to get as close as possible to the structure in the navigator. Yeah, you have here some basic objects, structure core, structure advanced, we call it in the API, types for nodes, types for lines, and so on, nodal supports. And everything what you can see here and navigate through it, we are trying to replicate as far as possible with the structure of the API itself. So you have also structure core, which is lines, nodes, members. You have the loads, the loadings, and you have types for nodes, nodal support. Yeah, and this is really corresponding to the structure you can see in the main program. Just to give you a better insight where to look for some objects. So how is it working now? We start by creating a simple node. When we made a new model, this is called create node. First, I define my node with the wished properties. And in principle, you can say we have two steps every time, or two separate roles. One is I'm working with model objects from the API. You can see here, this is a node using the structure core from the RFEM package. And this object here is used to define what I wish as a user to model in RFEM. And this node object is given as a gRPC message to my actual API call. The API call, we have not so many API calls like in our first generation. You can see the API call itself, it's very lean. We have calls to calculate, to create things, to delete things, to get things, save things. There are some specialities like a plausibility check and so on, working with the models I showed you. But this is it really. There are 30 by 40 maybe in the future API calls and a lot of objects to define and transfer. And all properties, all model objects are defined by these model objects API. So this is important to understand. I define my desired object and send it via this call to RFEM and let RFEM model it. So let's have a look on it. What's happening then? It is now modeling this special node, and you can see it worked. I got a node with the ID 48, and it has the desired coordinates I defined here as arguments for my desired node object. What if I want to update this node to get a feeling how this logic is working? We are doing the same, but this time the model is called a change node. We define the same node like the last time. It has the same coordinates, the same properties, and create this one as well. What we are doing after that is I create another node, and I call it the same. It's now it's the next idea of my node. This object and this object isn't related at all. It's just I make a new wish. And my next wish is that node number 48 should have 6.66 as coordinate 1. If I would create that node again, RFEM would say, oh, no, you can't do this. Node number 48 is already existing. This is prohibited. For this reason, we use the update API function. And when I update an object, I transfer this new wish here to RFEM, and it checks, okay, this is another coordinate, and we will model it with the desired properties if possible. So if we are doing this, we should see at first a jolt numping from left to right. You saw it, jump from here to here. And now the node number 48 has the updated coordinate for X. So what if I want to call some properties from RFEM? Again, we create our famous node 48. And now I'm asking RFEM, okay, I want to have information about this object you have in your program. So I'm using the getObject method. Everything I show you here is for a single object. We have a special call, respectively, if you are working with many objects, and this is an important difference. So please have in mind, there are calls for working with one object, and there are calls for working with a lot of different objects. So for now, working with a single object, I give a new object here and ask, I want to have an object back. And this object is described as a node with the ID 48. Again, this is another model API object than we defined here initially. And this is used as, you can see, as a dummy node to give RFEM the information. What do you want to have? I want a node with the number 48. What we are doing after that is, show me what you got as an answer. We store this information in node 48, print it, and work with the coordinate here. So you can see the properties here. What we got back is it's our own definition. It's our own class built in the API. It's an element we got back, which is from the type defined in our API as a node object. And if you print this node, you can do this. This is the information which RFEM delivers you over your API. We have the coordinate 1, 2, 3, which we defined here, but there are also some other informations, like, for example, what type is this node? It's from type standard, obviously, because I never said what type should you be. Is it type on member? Is it a standard type? Whatever. RFEM has some default values, and it's using them dynamically if you don't define them in your wished object. It's choosing a coordinate system if you don't do it, and has also some other internal informations which are used to check if something is generated or updated and so on. It also retrieves the comment, and since we do not define a comment here in RFEM, it's an empty string. But you can see there are more informations than we define if you call that by RFEM. Okay, these are our basic functions for single items. There are also some which exist if you're working with more items than one. And this is a new style of working with our API in comparison to our first generation. So this is an important change and also a big reason for our speed improvement regarding the processing of informations. In this example here, we are now creating many nodes. And we are doing this by using one call. And this call is create object list. That's everything. And with this call, we will create 1,000 nodes. And this 1,000 nodes are defined via a helper function I wrote by myself here. It is just a list of node objects. And what is remarkable here, I'm using the RFEM structure core node object here. And you can see for this example, I don't use an ID for this. I just say, okay, this is a node object. I don't know what ID it is, but it has a coordinate X, Y, and Z. And I'm doing this by iterating here over a range, which generates me some coordinates for nodes, for 1,000 nodes. And what I'm doing here is every generated node object is stored in a list, this list of nodes. So what this is returning here is a list of 1,000 node items defined by our model objects API. And this list is handed over to the function create object list. And now you can see what's happening. Yeah, it will create all these 1,000 nodes in one step. And this really is important to work faster and maybe more structured with our new API here. So what do you do if you want to update these nodes now and make something else? Since you don't have an ID of your nodes, because we created them dynamically without giving an ID, yeah, you can do this. You don't have to use it. Also, you could give them an ID and just work with this later on. But just to show you before that how to work with get many objects. At first, we are doing the same like in the last example. We are creating many nodes via one call. And what I'm doing here now is I want to have an object ID back. Yeah, we set up this optional argument to true, that this create object list call is giving us a node list back. And in this example, we will hold the console output for several times and have a look what is happening here, because we are working with this list later on. What I show you here is something we are improving in the next weeks. So in a few weeks, maybe it is not necessary to work with this steps in between here, and maybe we are able to get some objects directly back from this call, but this is work in progress. For now, in the actual version, if you try it out here by yourself, you have to work with this, with this workflow here I show you now. So let's see what is happening. Just open RFEM, create this nodes again, and what's happening right now is, we hold here, print and hold, and say, okay, show me this node list you returned. This also is a self-defined class in our package. It's not a dictionary, it's a special object from which is representing our object ID list. And this list here, this object has all the node IDs and says, okay, this is an object from type node. So this is a way to get back which ID is defined via this call for many nodes. Yeah, it answers with, okay, I create 1,000 nodes, and here's what I created. And the last one has number 1,000, and it was a node. Right. So if I want to manipulate these nodes later on, first I need to create an own list where I store dummy objects which contains these node numbers. And to make an iterable object from this returned node list, I have to add object ID after it. Now I can iterate over it in Python. And we will make a new real list, which is called dummy nodes. And for each item in this object ID list here, which is iterable, I will append a new object. It's a new node containing exactly this number here we see from this output. So after that, we have a list with dummy nodes. And let's have a look in this. Oh, isn't it working? Yes, no. Okay, now it's doing second and third one. So we printed the list with dummy nodes, and if you print a node and the only information it has is its number, it prints its number. So we have stupid nodes which has their number, and with this list I can do some I can work later on to manipulate them. But this is the first example, a workaround how to get numberings from a node definition at the moment. We are working on improvements about it. So if you have now the IDs, then you can ask RFEM, okay, give me the objects for nodes with this ID. And this is the last step here we just saw. This is corresponding to what you see if you get a single node information. Yeah, we are doing the same like here with an object list, with a list of node IDs. And we can see these are the informations for each node we have created with the many nodes function. So now we can also update a lot of objects at the same time. Like last time, it's an extension of the shown example. We have the returned object list, and I just made a helper function which is handling these object ID and making the dummy list for me. It's returning the dummy objects. I show you in the last step here as an own block. And they are stored here. So we create the many nodes, save the returned objects, make our dummy nodes. The dummy nodes is a list with the IDs of the nodes, get the object list from that, and store this as node objects. And then I want to edit those coordinates from these objects by a specific offset. And for this reason, I created another function which is using this a list of nodes. And yeah, I ask RFEM, okay, give me a list with all these nodes, which contains also the global coordinates and the IDs and so on. And this list, this is called the node objects, is handed over to the edit coordinates function. And it manipulates the coordinates by adding a specific offset to it. So I ask every node object in the list for coordinate 1. For example, here it's 3. And I'm adding 20 by that. And I make a new node, which is saying, okay, this node now, for example, this one would be here, node number 204, will have a new coordinate, which is now 23. And I put it in a list for node updates with new node objects. And with one call here, update object list, I will use these moved nodes to update 1000 objects at one time. So we see again, the node block is created on one place and then moved to another one. So now let's dive in finally into the small real-life example of a single span beam. We will use the principles we got to know in the first 2 chapters here, playing around with nodes, and now go for other objects as well to model a single span beam. If you look closer here, we are doing exactly the same like with the nodes. We will slightly restructure it here to make this work within our own create and calculate function here. The single span example is split it in create and calculate, processing of results, and a main script which is calling both of them by importing these unit examples here. Let's have a look into create and calculate. We will again define all model objects with one creational call, create object list, you know that in the meantime. And the specialty is that we are defining all model objects in one list, not only the nodes. So if you can see here, yeah, we have the same small import with Dlubal API RFEM, and we have the nodes, we have the line, we have material, section, and member. Everything in this structure you already are familiar with. So if you have the RFEM object here, we can see there's, for example, structure core, and you got all your typical items here you also have in the navigator tree of RFEM. Yeah. So if it differs, yeah, it's, for example, types for nodes, you can orientate by the structure in the RFEM navigator and see, for example, here the type. Oh, this is the completion is wrong in the meantime. Yeah, there's the types for nodes, for example, and then you can see the nodal support. And this is really the same structure you have also here in the RFEM program. So how to work with that? Best practice is to put everything in one list on one level of hierarchy. So let's make a simple geometry list, a simple member list, and so on, and add them together later on. Yeah, working with lists in Python is very flexible and easy. You can just add them, and this gives back one list with one hierarchy with every object from every single list defined. So to have a look on this, you can structure this as like you wish. Yeah, in my example here, I tend to organize it via geometry, and for example, for the member definition, I like to have a material, section, and member in one list, but you can do it like you wish. It's totally free. In the end, you need to ensure that every object you define is built up on another one maybe, and that you have the list in the right order. That, for example, a member which you are defining starts with a section which is already defined in RFEM. Yeah, here is a section defined for section 1. First, it is recommended to define the section with the informations you need. So if you need some types here, like defining what this member type should be, we have a convention that you can use these enumerates. You can alternatively also look in the documentation and say, oh, this is the type which you define with a string, or you use the enumerates. And the convention here is that if you need some specific type or property, you use the same object name here, and under that you have all different types, like for example truss, rib, cable and pulleys, which is coming soon. And here you can use the type beam to define it. And this is a nice feature that you are already in the same naming space here and can use enumerates. If you want to define material and section, maybe you know it from applications in the past, just go into these RFEM setting, for example, and try out what's happened if you look for a special string. What's happening here in the background is if you put a string as a name for a material or a cross-section, for example, RFEM is looking up for the first option it finds and uses them later on the program, so you can check it on the fly, what is what. So in this way, we also define the loadings, design situation, static analysis setting, load case, member loads. Remember, it's defined in SI units. And why is it important to define everything from scratch? With this call here, I delete all existing objects in the RFEM model. And you know it by default, if we create a new model, here are some objects and load cases which come as default. And with the delete all objects call, every one of these objects is deleted. So you have to make everything from scratch. And as well as here, as so in the examples on our website, you can see different types, not only the nodes I showed before. So you can have a look later on, or every one of these unit lessons here will be provided after the webinar for you. So once you defined the object and created it, we will perform something new. We will make a plausibility check. And you can define the type by enumerate. We want to check the calculation logic. And we print it. What is the result by that? And if this plausibility check is true, then we run calculate all. So in this state of development here, we can run a calculation. And also we will get the first results. Which results we are getting is defined as well by a property here for this get results call. And this is also an enumerate. And by today, we don't have everything what we want to have for result tables here implemented, but there are some enumerates which are already working. For example, the results from static analysis for member internal forces. And what we do in the end is, which is nice and a handy feature here in Python, you get back with the data option here, a Panda data frame. And with a Panda data frame, if you're familiar with Python, you know it's a very mighty and powerful module to work with big data and structures and series and so on. And I will use the Pandas data frame option to store it in a CSV file at the end of this call. And later on, we will read these results in and work with pandas data frame functions to set an index, sort it, analyze the maximum results here, just to give a first look how to work with results from our program. And the result format you will get, it's more or less directly orientated. This is the CSV we will get. It represents the table you can also view in RFEM. So the whole structure of getting results and so on is based on the structure here we get in the results table too. But let's see what happens in the program if we start it. So what happens here in the background, you can see it on the right side as well. The plausibility check was successful, true, so the calculation just started. You can see it here, bottom left. And now it is getting the results, processing them, and is printing out what we defined here in our little process script, just to give you an idea how this is working. And let's check what we found out. If I go to the surf rate here, activate the results, we looked for the maximum bending moment over of the y-axis. So it's 3.95 here in SI units, Newton meters. On the position X, 2.5 meters. The whole beam here is 5 meters. So this is plausible. And you can see if we have the results table for static analysis. And go, for example, in the results by member, this type of presenting the results and the internal forces here, this corresponds with the logic the CSV file is built up in the background. So if you get the results, it's more or less orientated to the logic you see in the result tables. Again, we try to make it as much as comparable to the RFEM structure, like with the navigator for input files, for input objects. So what do we have as a maximum object? 42.83, and we found the same value in the CSV files. So that worked quite well. And yeah, now you got an idea how to work with a full case of a small model. Calculate all is one of the API requests which costs Dlubal credits. And you can see if you perform this action, you will see a new API request in your extranet and see we used 1 credit for 1 solver run. So have this in mind when you need to check which call was requested for some credits. So in the final minutes, I will switch to another 2 examples. Just a quick glance on the steer frame here, which showcases how this could look like in a more class-orientated implementation. Because what's important to say, you don't have necessarily to work with the with statement and RFEM application. Of course, it is also possible to write your own class, for example, and open the connection within this call. But then you have to handle to close the connection as well, to ensure that RFEM opens and closes in the with statement. It is managed by Python then automatically, because the implementation of our application method here is handling this together with the with statement. But if there is a need to define your own classes for testing or for productive use, feel free. And you can use then your, for example, own model manager, which is opening and closing connections with your own set of code. And yeah, it's quite another style here. You figured out by yourself. You can also make your own classes for frames and so on, for calculation of nodes, for members. Yeah, just to say it's not necessarily to work with the if statement. So let's see how this is going. of course, the connection then opens and closes as well. And here in this example, I used a class for a frame to model two different frames, which build on an own class I have wrote and with separate properties. And you can play very creative, defining your own classes, your own model definitions, put some complicated logic inside. And what's really nice about it, here in the frames, there is no single API call included. Everything will be then handled in the model manager by transferring an object list to actually build these objects. And in this example here, I also, because I don't like to repeat myself every time to make plausibility checks, etc., I just built in here a method which automatically performs a plausibility check. And so you can automate your workflow like you wish, so that this tries to calculate, and if the plausibility check in this case is not successful because the model was not supported, we see it here, we just built the frames but with no support, then it doesn't calculate and everything is handled well and the connection is closed because it wasn't successful. So just to get an idea what is possible with that. And finally, we will have a look on the steer frame, which my colleague provided me, thanks to Robert Milrat. So let's close here this model and switch to this project. We prepared this in a way that we will see our own graphical user interface. So let's see. Here we see this graphical user interface, and I will open RFEM in the background. So just to give an idea, you can do whatever you want with input values. You can do whatever you want with the results you get from our API. So just as an interpretation here, what is possible, you see you can program yourself a UI, web application workflow, a database workflow, whatever you need. And if we create this parameterized steel hole here in the background, you will see there is a time-consuming progress opening a project file. This is what you can see here. This is at the moment what is taking some time. Once the model is opened and the data is loaded, it will be very fast to model all these entities we defined in the program. So you will see the performance speed advantage also on this model, but don't get confused about reading data here. This is not the API call, which is taking time right now. Now maybe we have a look into this further, how we can improve the preparation of this model. So, but preparing, reading the data takes some time. Soon, in a few seconds, the model should open, and then the actually usage of the API starts when it's modeling the steel hole. So once the model here is opened, which is taking some time. So we loaded the array. Now it's opened. And it generates now the objects. So I misclicked it. Here you can see it. We see the parameterized steel hole. And just to get an idea about a second run with different parameters, you can obviously choose your own values here, make different settings about it, just to play around a little bit with it, get an interesting geometry. You see, this can also be fully automated in the background with a headless server version. So feel free to use your fantasy and creativity to create own workflows. And obviously, let this here load in the background again. We jump into the results later on. it would be very nice to go with it now in the next step and to set up some add-ons and load assistance. This is one of the next steps we are implementing for the API. So we are trying to enhance the result tables so that every important option getting the results in the program. So now you can see once it plopped up here, the model opened and it modeled. This is the speed of the API, which is much more faster than the loading process of the template here. So yeah, you can see it worked. And what needs to be implemented in the next step is really manipulating with the API these base settings here, that you can activate different add-ons. In fact, every register here, except for the terrain. Terrain is a model object to steer this and use add-ons and also use the load wizards in combination with the normative standards. So this is some of the next step. And also for the Python API, we will allow the manipulation of some objects which are used in the manual operation with the graphical user interface. So there will be a special version in the Python API to use these manipulation functions also via code. So it's more or less interactive then, and you can react to the model and use the copy feature to create those frames or other things. And this is currently in development. And also good news for those of you who are using the C# client in the past. Since we are using gRPC and protobuf, it is technically possible to build your own C# client. And we will do this in a basic version for you. And currently we are thinking about how to provide it, where to give you the package. And in the future, we will try to give this as a second option to the actual Python solution we already offer. And after we did those basic steps here for RFEM 6, of course, R#9 follows as a second big application. We will implement the API. So stay tuned. Have fun with this. Thank you very much for listening and your attention today. And regarding on the time, thank you for staying a few minutes longer with us here. And yeah, you're welcome to ask your questions and we are happy to help if we can. So have a nice day then, and back to Andreas.
Thank you, Florian, for your presentation. I have a last hint. You can book our online courses, for example, for RFEM 6, it's a course for beginners, or Eurocode 2, the reinforced concrete design, Eurocode 3, steel design with RFEM 6. For more information, just scan the QR codes or press on the buttons at the bottom with the links. A new course is the Eurocode 5 course for timber design, and also new are the packages. You can book such a package with the Eurocode 2, 3, and 5 course. And this package contains also RFEM 6 and the Eurocode courses. Okay, that should be also all from my side. I thank you for your attention. Thanks again to Florian for the presentation. I wish all a nice rest of the day. Maybe we meet each other in a future webinar. Bye-bye.